Lesson 5.4, Part B. Now in this part of the lesson we're going to talk about using our calculator to calculate some more specific and better data, better numbers and more accurate numbers. Similar situation, we have the year for zucchini lengths and the length in which they were recorded. We're asked to make a scatter plot of the 10 data points. Let X represent the number of years after 1985. Now it's important because that means that 1986 is 1 year after, 1987 is 2 years after, and so on. So we would say 3 years, 4 years, and those represent our coordinates. So 1 and 31.8, 2 and 32.9. So again, years after 1985. And Y represents the winning length that year for zucchini. We'll then use technology to perform linear regression, and what is the equation from that model? We'll get that, and then we'll graph it approximately. Alright, predict the winning length for the year 2000. So once we have that equation, we can predict the year for the year 2000. Now again, we're talking about years after 1985, so the year 2000 would be 15 years after. Okay. So if we look at our graph, again we have a squiggly mark here, and that's okay. We're not going to let that bother us at this point because we're aware of it. So 1 gives us 31.8. So about 31, about there. 2 is 32.9. 3 is 30. Now again, don't have to be in a line, so right now it doesn't look too good about being linear. 4 gives us 32.7. So we're about there. 5 is 34.2. 6 is 33.6. 7 is 34.5. 8 is 36.3. It does seem to be getting larger every year. 9 is 34.4. And 10 is 35.5. Now, this looks a little bit more scattered. But again, our data tends to be going this way. Okay? And this is an important part of the process here because some would say, you know what, I think it looks more like this. And some would say, no, I think it's more like this. Alright, so because we have all these different opinions, there's a method that's called the least squares method that looks at the difference between the line and the actual data point. So it looks at all these lengths and it takes that difference and it squares that difference and adds them up. And the line that comes up with the smallest number is said to have the least squares result. So it's called the least squares line. So it's trying to make the distance between all those points, the sum of all those distances, as little as possible. Alright, so how do we do that? Well, we got a calculator and we plug in the list 1 and list 2. So if you're familiar with what we've been doing in the past, I list 1 through 10 on the left, I list the numbers that correlate with that on the right in list 2, and then we would go stat calculate, and I'll show you that right here. I don't have the data in there, but I'll show you how I use my calculator for it. Alright, I'll clear this out, and once my data is in there, I would go stat, over here, I go stat, I arrow over to calculate, and I have linreg ax plus b, and there's also one further down. It says linreg a plus bx. Same result, but just ordered differently. So I use that one, and we would just go enter, and then you'd have list 1 and 2 in there, which if you just have those two lists in there, it defaults to that, and you'd go enter. Okay? And that would kick out this information. Now notice that it has y equals ax plus b. It tells you a, it tells you b. So you'd say y equals a, which is 0.4, I'll go 9. The longer the decimal, the more accurate the answer. X plus b, which is 30.92. I don't know what just happened there. Oops, my color changed. Alright, 30.92. That's the y-intercept. Now our graph jumps down here, but it's about pretty close. 30.92 actually would put the line up here somewhere. Oh, 30.92 actually right about there. So my line that I chose is not the right line. This one gives you a better result. Now it says to calculate the year 2000. Now 2000 is 15 years past the year 1985. So you'd plug in 15. I don't know why I get that color change there. That's strange. Okay, so being funny with me. So y equals, and I would then crunch my numbers, and I would get 0.49 times 15 plus 30.95. And I get 38.3. Now what this does is it says that, you know what, we predict that if the pattern is consistent, that in the year 2000 you will have a zucchini of the length 38.3. Now sometimes that makes sense, sometimes that doesn't. Some would say no way would a zucchini ever be that big, but the trend here shows that it's possible. We know, however, that in real life, if you do height, if you grow 2 inches a year, you're not going to keep that rate consistently. You will eventually slow down and stop growing. So some things don't work past a certain amount of time. Now notice there's two things here, r squared and r. The r is the correlation coefficient that we just talked about. The correlation, the measure of linear relationships. 0.8 is very good. We said it goes from negative 0.1 all the way to 1. 1 is a perfect positive relationship. 0.8 is very close. R squared is an explanatory version of correlation, which we won't get into. So we mainly look at this. Now if your calculator, if you have a TI and it does not have that when you do this calculation, then you have to do something. And that is basically, and I'll show you how to do that. You would go to catalog, so second function, catalog, and you'd go down to D. I'm going to type in the letter D here. Jumps down to D, and I go down to diagnostics on. So if I don't have it, I would click on diagnostics on. I would do it again, and I had that thing on there, so ignore that. So if I go again, and I go down to diagnostics on, enter, enter. Next time I do this calculation right here, I will get r and r squared. And again, r is what we were looking for. R is correlation, and that's what we're focusing on in this lesson. Okay. Now, what does correlation tell us? Now, this is our quick reference before we're done. We said correlation is between negative 1 and 1, but this is a nice visual to show what types of data will give you what values for correlation. So notice here r is 0. The data is scattered all over the place. As one variable changes, the other one changes without relationship. Correlation is 0. And if I go down to a correlation of 0.5, it looks a little bit better, but 0.5 is not that great. When you get to 0.9, again, 1 is perfect, which would mean a straight line. 0.9 shows that you do have a pretty good relationship there. On the other column here, we have negative relationship, and that's the only relationship to slope that correlation has, positive and negative. Otherwise, it doesn't relate at all to slope. So here we have a negative 0.3. So negative means a downward trend, but 0.3 is not very tight, not very narrow. Negative 0.7, pretty good. Negative trend, true. 0.7 does have linear, better than 0.5, but not as good as 0.9. And then we have a negative 0.99, almost a 1. And you see how linear that is? That looks very good. So it measures how linear your data are, how close to a straight line they are. And again, it's a straight line relationship. We do not use linear, we do not use correlation coefficient with data that goes like this. That looks like a parabola. That's nonlinear, and a correlation coefficient would not work in this case because correlation coefficient is a linear value. Okay, so causation is our last piece. What does causation mean? Well, people work hard to get this scatter plot and to find a linear relationship to say, you know what, one variable causes another. And that's why we are calling the x value the explanatory variable, and then the y variable the response variable. How does that respond to the explanatory variable? And a lot of people want to make the connection and say one causes the other. It may have a good correlation, meaning it's very linear, but it does not always mean that one causes the other. And a classic example of this is to compare shoe size with reading ability. Okay, like say your reading skills. On this graph you have a very strong linear relationship. And the linear relationship shows that, you know what, as your shoe size increases, so does your reading skill. And we know that the graph says there's a relationship. The graph seems to be telling you that shoe size causes reading, but that's kind of absurd. Shoe size does not dictate whether or not you're going to be a good reader. We know that there's other things that play there. So what this graph has is what's called a lurking variable. And that means the variable that is binding these two things together to make it look like one causes the other, but actually it's the lurking variable that is the key. And when you compare these two things, the reason that as shoe size increases and then the reading increases, the lurking variable is age. So you personally will become a better reader as you get older, and along with that your shoe size will grow because you're growing. So it's not the shoe size that caused the reading to improve, it's your age. So that's called a lurking variable. So do not always assume that there's a causational relationship here when you have a good linear relationship. You always want to look at it carefully to decide if it's the case or not. And that's where studies come in, where hospitals will look at do studies and experiments, that's called experimental design, to clean out all the lurking variables to actually know what causes what. Very important with medicine. Alright? And the key here is that correlation does not mean causation. And this ends lesson 5.4, part B.